Let's decode the result of this given equation involving logarithms. We have here the logarithm of x plus 6 to the base of 3 minus another logarithm out of the quantity x minus 2 to the base of 3 is equal to 2. Let us try to solve the value of the variable x, which could satisfy this given equation without any use of any calculators. To do this, we need to understand the operation separating the two logarithms, its subtraction. And since the two logarithms share the same base, the base of the first logarithm is 3, the base of the second logarithm is also 3, we can apply here one of the important properties or theorems for logarithms. This is when you have the logarithm of a to the base b, and then you will subtract another logarithm, let's say c to the base b. This is only true if the bases of the two logarithms are the same, and under subtraction we can just simply write them into one logarithm in the use of the same base, but the coefficients a and c will be under the process of division. This is one of the important properties of logarithms. But given that the value of c on the second logarithm, or the value of c, which is the denominator of this expression, is not 0, so that it will not be undefined as a whole. So for this, we can rewrite our logarithms here. So let me rewrite here the logarithm of the quantity x plus 6 to the base 3 minus the logarithm of the quantity x minus 2 to the same base 3 equal to 2. The entire left-hand side can be rewritten into one logarithm of the same base, which is a 3, and you will be having x plus 6, the first coefficient, to be divided by x minus 2. This would be entirely equal to your right-hand side, which is 2. So this is what we did, and we combined the two logarithms into one. The next here is the transformation of any logarithm a, let's say to the base b, is equal to, let's say, another variable y. We will not be using x because x is already there. We can transform this into an equivalent exponential equation following your b would be the same base, the equivalent of the entire logarithm as the exponent of the base b, which would be equal to the coefficient a. So following this property here, this is just equal to, we will be using the base of 3 here. The equivalent would be its exponent 2 is equal to the entire coefficient here, x plus 6 over x minus 2. And from this, we know that it's 9 is equal to x plus 6 all over x minus 2. So from a logarithmic equation, following this theorem and this property, we're able to come up with an expression here. Now, when we are going to solve for x, let's multiply both sides by the denominator x minus 2, so that this would be cancelled here. And again, multiplying both sides by x minus 2, so that we retain equality. This would mean that your left-hand side would be 9x, you distribute 9, minus 18 is equal to x plus 6. Then linear equation, subtract x both sides and add 18 both sides. You'll have 9x minus x is equal to 6 plus 18. You'll get a result of 8x is equal to 24. Therefore, the value of x, which could satisfy the given logarithmic equation, is equal to 3. This is the result, and we can verify it by substituting our given in our equation, and you could do that on your own. But we did this by understanding the concept of the difference of two logarithms, which could be written as the logarithm of a quotient. And then out from that, we apply this property to come up with a linear equation. And with this, we have decoded now the value of the variable. And that's mission accomplished.